Okay, today we're going to start off by talking about the continuous uniform distribution. So an important difference between discrete and continuous variables is the way the probability is defined. We already know that discrete is counted and continuous is measured, and discrete is like start and stop, and continuous can have everything in between it. But in a probability distribution for a discrete random variable, each possible outcome of the random variable is assigned its own probability. However, if we did that for continuous random variables, it wouldn't work because there are infinitely many outcomes and each one has its own probability. So for discrete, it's counted. We can take each one of those values and we can assign it a probability. But for continuous, there is absolutely no way that could happen. There's too many outcomes. Therefore, continuous random variables do not have a probability distribution function because of the fact that there's too many points. If we attempted to assign each value, even an infinitesimal probability, the sum of all the probabilities would definitely be greater than 1 because continuous has too many variables. Okay? This means that for continuous random variables, probability can only be assigned to intervals, not each individual value. So a good example of what this looks like is right here, the continuous uniform distribution. We're going to give it an interval, and this interval is going to be from A to B. Okay, so we can't do each individual value. It has to be from A to B. Now the height is already determined. It's going to be 1 over the difference of A and B, so B minus A, 1 over that. So the uniform probability density function is given by this formula right here. 1 over B minus A for any value in between A and B, and if it's not, then it's just 0. And then the mean and standard deviation also need those A and B values. That's the beginning and the end of our interval. The mean of it is just adding the A and B together and divide by 2. And the standard deviation is B minus A over the square root of 12. Okay? Now, since continuous random variables cannot have probability distribution functions, they instead have probability density functions, which is where this comes from. Okay, we can't have a probability distribution because there are too many points. We have a probability density function. When this is graphed, it produces a rectangle. You can then find the probability of observing a random variable in a given interval by finding the area of the resulting rectangle. So let's give this a shot, and we're going to work out how it works here. First of all, it says the fire department records how long it takes each of its trucks to reach the scene of a fire. Suppose that distribution of arrival is uniform with the minimum time being 2 minutes and the maximum time being 15 minutes. Let x equals the time it takes for a truck to arrive at the scene of a fire after being called. So you've got to think about this here. It says we're talking about like arrival time of a fire truck, and it goes between 2 minutes and 15 minutes. Well, that's definitely going to be continuous because you could be there in 2 minutes and 30 seconds, 2 minutes and 30.123 seconds. Like it has to be continuous, which means we're going to have a probability density function. Okay? Now, what they're saying is the minimum time is 2 minutes and the maximum time is 15 minutes. So if we were to draw this probability density function, it's going to look something like this. It's going to start at 2 minutes and it's going to end at 15 minutes. Okay? Now, they say that it creates a rectangle. However, the rectangle has to have a predetermined height, and that predetermined height is going to be 1 over B minus A. So 15 minus 2 is 13. So that predetermined height is going to be 1 over 13. Okay? Now part A says, what is the probability that a truck will reach a fire scene within 5 to 10 minutes? So this is my density function, and they want to know what's the probability that it's going to reach there within 5 to 10 minutes. So we're not starting at 2 and ending at 15, we're starting at 5 and ending at 10. So 5 is going to be right about there, and 10 is going to be right there. They want to know what's the probability that it's going to arrive in that interval from 5 to 10. Well, to do that, we just have to find the area of this little rectangle. Okay, so the area is going to be length times width. So right now it's 1 over 13 units high times 5 to 10, which is 5, and that's going to be 5 over 13. So the probability that the time is going to be in between 5 and 10 is going to be 5 over 13. Okay? Part B says, what is the expected time until arrival of the fire truck? Now remember, expected time or expected value is the same thing as mu. Okay, the same thing as mu. So to find mu, we just use that formula up above, and it says mu is a plus b divided by 2. So a value is 2, and b value is 15, and we're going to divide that by 2. Well, that's going to give me 8.5 minutes. So the expected time until the arrival of a fire truck is about 8.5 minutes. And part C, what is the standard deviation of the truck arrival times? Again, we just use that formula that they gave me. The standard deviation is going to be b minus a over the square root of 12. So that's going to be 15 minus 2 over the square root of 12, which is approximately 3.753 minutes. Okay, the standard deviation is about 3.753 minutes. So that's what we've got for probability density functions. Okay, so number 2, it says the annual growth in height of cedar trees is believed to be distributed uniformly between 6 and 11 inches. Okay, so again, this is going to be continuous because you can be 6.1 inches, you can be 6.12 inches, you can be 6.125 inches. It's going to be continuous, which means I'm going to sketch a little picture of what it's going to look like over here because I'm just a visual person. And it says it's going to be uniformly distributed between 6 and 11 inches. So 6 and 11 inches. And we're going to have that rectangle. Now the height is going to be 1 over b minus a. So 11 minus 6 is 5. 1 over that, which is 1/5. That's my height. Okay? That's what we've got for a probability density function there. Now, part A says, what is the mean growth per year? So again, that's mu, and we just want to add them together, 6 plus 11, and divide by 2. And that's going to be 17 over 2, which is 8.5 inches. The mean growth per year is 8.5 inches. Part B is, what is the standard deviation of growth per year? And again, from that formula, it's going to be b minus a, so 11 minus 6, and we're going to divide it by the square root of 12. So go ahead and pause the video and put that in your calculator. And you should get about 1.44 inches. 1.44. Part C, what is the probability that a randomly selected tree will grow between 9 and 10 inches? So the probability that a randomly selected tree is going to grow between 9 and 10 inches. So that's going to be just like our fire truck problem over there. The area is going to be the difference from 9 and 10 because it's going to start at 9 over here and end at 10. So it's going to be 10 minus 9. And we're going to multiply that times the height, which we already said was 1/5. So 10 minus 9 is 1, times 1/5 is just 1/5. So the probability that a randomly selected tree will be between 9 and 10 inches is 1/5, which we know is 0.2. 0.2. Okay. On letter D, what is the probability that a randomly selected tree will grow less than 8 inches? So the probability that a randomly selected tree will grow less than 8 inches. Okay, so to do that, that means less than, since it says it's distributed between 6 and 11, that means the lowest we can go is 6. So that means my rectangle here is going to start at 6 and end at 8. So the area is going to be 8 minus 6 because that's going to be the width of my new rectangle. And again, we're going to multiply it by that 1/5. Well, 8 minus 6 is 2 times 1/5 is 2 over 5. So that's going to be 0.4. 0.4. Letter E, what is the probability that a randomly selected tree will grow more than 9 inches? So that's going to be x is greater than 9. So that means my rectangle here is going to start at 9 and it's going to end at 11. So my area is going to be 11 minus 9, again times 1/5, which is again going to give me 2/5, so 0.4. And letter F, what is the probability that a randomly selected tree will grow exactly 7 inches? exactly 7 inches, even though my typing there is abysmal. Exactly 7 inches. So exactly 7 would be right here. Okay, that's exactly 7. Now remember, to find this probability, we have to find length times width. So if I'm doing exactly 7, there is no width. There is no range. And if there is no range, we would literally be taking nothing times the height. Well, nothing times the height, the probability that it's going to be exactly 7 is going to be 0. Because remember, this is a continuous function. This is continuous here. So there's the chances of it being exactly 7 inches are so small that it's basically 0 because there is no range. Now, while density functions for the uniform distribution has a flat top, a histogram of data from a uniformly distributed random process will not be so perfectly flat. Okay, so like we have one rectangle here, and that's going to have a flat top. But if I put them together and make a histogram with the intervals, the ranges here, it's not going to be so perfectly flat. The graph below shows 100 observations of a random process that was uniformly distributed between 2 and 15. Clearly, the frequency of each category is not identical. However, if you up the observations to 1,000, you can see that the distribution would begin to level off. So if you'll notice, when we have 100 observations, it's kind of a little bit wonky in here. You can see that it's not like perfectly flat like we were dealing with in the past, but it's a little bit wonky. But when you up the observations to 1,000, it kind of gets a little better. They're all kind of like leveling off. And the higher the observations, the closer it is going to be to perfectly flat. So you can notice that by just the number of observations. Okay, next what we're going to talk about is the normal distribution, otherwise called the Gaussian distribution. Sometimes you'll hear it that way. It's bell-shaped, but just remember that bells can come in various shapes and sizes. So like bells can look like this, bells can be high. So it is bell-shaped, and they are all symmetric. And since they are all symmetric, the mean, median, and mode are all equal. That's really important here. Since they are all symmetric, the mean, median, and mode are all equal. So let's talk about properties of the normal distribution. The total area under any normal curve has to equal 1, just like probability. Within a fixed number of standard deviations from the mean, all normal distributions contain the same fraction of their probability, and the probability of a normal distribution or a normal random variable being in some interval corresponds to the area under the curve bounded by specified intervals. So over here we have these 3 intervals, and these are just like the empirical rule where it was 68, 95, and 99.7. However, it's just more specific. You'll notice that it's not just 68, it's 0.6826. And here it's not just 95, it's 0.9544. So it's just a little bit more specific. So on the next page, what we're going to do is we have the normal curve here. We're going to put each measurement in these so you guys can use it to help you on your homework. So again, just a reminder, since it is symmetric, the mean, median, and mode are all equal. That's really important, and that is right here in the middle. And if you go 1 standard deviation to the right, 2 standard deviations, and 3 standard deviations, and then the same thing as -1, -2, and -3. So from this normal distribution, again very similar to the empirical rule, from this normal distribution, it tells me that from -1 standard deviation to +1 standard deviation is 0.6826. And what you're going to do is you're going to split that in 2. You're going to take that 0.6826 and you're going to divide that by 2, and that's going to give me 0.3413. That means 0.3413 goes on each sides of these. 0.3413. Okay? Now, from 2 standard deviations away, we know that that has to be 0.9544, 0.9544. That's from here to here. There is 0.9544 of this curve from here to here. But we have already allocated 0.3413 and 0.3413. So what I want to do is I want to take 0.9544 and subtract that 0.6826. Okay, I want to take away that part that I've already used, and then I'm going to divide that by 2. And that's going to give me the individual measures for both of these little pieces over here. So 0.9544 minus 0.6826 divided by 2. Put that in your calculator. Pause the video, put that in your calculator. And you should get 0.1359 for each one of these guys over here, 0.1359. And then from -3 to +3 standard deviations, we know that that is going to be 0.97 or 9974. So since from -3 to +3 standard deviations is 0.9974, we're going to take that 0.9974 and we are going to subtract, so that's from here to here, we're going to subtract what we've already allocated, and that's going to be 0.9544. And then again, we're going to divide that by 2. So pause the video and get that done. And that should give you 0.0215 for each side, 0.0215. Now, to get the final little tails over here, a lot of people panic because they're like, well, they didn't give me a number for like what it would be past 3. Yes, they did. On the last page it says the total area under any normal curve has to equal 1. It has to equal 1. So what we're going to do is we're going to take 1 minus from -3 to 3, which is 0.9974, and we're going to divide that by 2. And again, that's going to give me 0.0013 for each one of those little tails, 0.0013. Now, just having this right here is really going to help you on your homework so you don't have to redraw it every time, and you guys can see the values. The normal probability density function is given by the following. This is really intense, okay? Like, it's weird because it says normal probability. It's much less normal than the uniform function, in my opinion. It's bonkers. It's bananas. Okay, so it's f of x equals 1 over the standard deviation times the square root of 2 pi times e to the power of negative x, which is just the given value, minus mu squared divided by 2 times the standard deviation squared. That is the formula for the normal probability density function. And again, I do not think that looks very normal. So let's talk about this. We have some normal curves here, and I want you to know, remember, it said that normal curves can come in all sorts of, or like the bell shapes can come in all sorts of different shapes and sizes. So here, you'll notice that they are all the same height. They're all the same height, but they tell you that their means are different. So the mu here is 0, the mu here is 3, the mu here is 7. All of these curves right here, they have the same standard deviation, but they have different means. Okay? They have the same standard deviation, which is why they look almost the exact same. They just have different means, so they're like shifted on our number line. Over here, we have 2 normal curves that have the same mean. Notice the center of their curve is both at mu, so they have the same mean. But this one is like short and flat, and this one is tall and skinny. That means they have different standard deviations. Okay? Standard deviations are the ones that create their actual shape. So, in the examples below, notice how these samples, taken from a normal population, show a faint resemblance to a bell shape. However, samples can be unpredictable. So even if the population is normal, you know the population is normal, samples can be really unpredictable. The larger the sample, the closer to a perfect bell curve you're going to be. So here we have a sample of 25. It's a little wonky. It's not very normal. But if we increase, again, here we have the sample of 25. It looks a little closer, but again, that just shows how if you get the wrong sample, it can really give you the wrong the wrong information. But as we up the sample size and we get closer and closer to the size of the population, your graph here is going to be closer and closer to a normal bell curve.